In this video, we're going to talk about systems with varying mass. Now, this is one of those things that I tell you guys, it's not incredibly important for the AP test. It's very interesting, and I want to show you guys the equations and how to use them and how they're derived. But I would write them down, and put a box around them and definitely know how to use them. But it's almost one of those things where I don't know if I would actually take up the brain power to memorize these equations for the AP test. Okay, it's up to you, but it's one of those things where if it shows up, it's like you can take the hit on that. You can lose a couple points if you don't remember these equations and use that very, important brain capacity for other things on the AP test that are much more important, right? That being said, let's talk about systems with varying mass. So in the previous examples with our conservation of momentum, we have done examples with masses that stay the same. Okay, so we have collisions, velocity is changing, but mass itself isn't changing. However, sometimes mass does not stay the same. An example of this would be a rocket that's burning fuel, right? That fuel makes up a lot of the rocket's mass. So as the fuel is burned, it loses mass, and therefore the velocity is also a function of the rocket's mass. So as the mass gets smaller, the velocity is going to get larger as well, because we know that the inertia of the rocket is decreasing, and therefore it's easier to accelerate forward. So when a rocket launches, most of the mass is in the fuel, which will eventually be burned and ejected from the nozzle of the rocket engine. And in order to solve these problems, we will apply Newton's second law to the rocket fuel system, not just the rocket alone. Now, an important thing to note here is that you can't just apply conservation of momentum and say we have an initial mass and a final mass, because again, it's a little bit more complicated than that. The velocity is a function of the changing mass. It's not just as simple as mass initial, mass final, V initial, V final. So that's why we have to do it kind of an interesting way, a more complicated way, if you will. So first, I'm going to show you how we find the acceleration and how this equation that we're going to derive looks very similar to Newton's second law. So here's our situation here. We have an initial and we have a final. In our initial case, we have big M. This is the mass of our rocket. And then we have our initial velocity of the rocket. Now, of course, this big M is made up of the rocket and the fuel. Then as the fuel burns, that mass M is going to change. Now, it's going to change by this dm, this change in mass, okay? So our dm is the change in the mass of the rocket. Now, of course, it's losing mass. So really, this is a negative quantity here, which is why we have to put a negative back here. So we have m plus dm. Now that dm will be our final mass minus our initial mass. And of course, like I said, initial mass is going to be larger than the final mass of the rocket as that fuel gets burned. So dm itself is going to be a negative quantity. Mass final will then, in the way that we're writing it, be dm plus mass initial, which of course is just m plus dm. So this term right here, negative dm, that we have to slap a negative on there because dm itself is going to be a negative quantity. And then of course, this right here is going to be the mass of the fuel that's ejected out of the back of the rocket. U right here is the velocity that we're observing of that fuel. And then our new velocity of the rocket is going to be v plus dv, where v is the original velocity, and then we have an added change in velocity there as well. So again, same picture right here. And now what we're going to do is we're going to apply the conservation of momentum to the rocket fuel system. So we have an initial momentum equals final momentum. Our initial momentum is just big M, our total mass of the system, times V, initial velocity. And then our final momentum is made up of the momentum of the fuel, which is the mass of the fuel, negative dm, times U, which is the velocity of the fuel, final velocity, plus the final momentum of the rocket that has burned some fuel. So we have the final mass of the rocket and the final velocity of the rocket. Now what we're going to do here is we're going to use relative velocity to simplify this equation. So relative velocity, we're talking about, remember we talked about relative velocity before and relative motion before. So what we need here is the velocity of the rocket relative to the frame. And so this is what we are observing this rocket going. That's going to equal the velocity of the rocket relative to the products. And then plus the velocity of the products relative to the frame. If we remember our subscripts for relative motion, this would be like velocity sub RF, and that would equal velocity sub RP plus velocity sub PF. And then remember, P is the last subscript in the first term and the first subscript in the last term. So since it's at the middle, we cancel that out and we get velocity of the rocket relative to the frame. That was a long time ago at the very beginning of this class. Don't worry too much if you don't really remember how to do that. It is a little bit confusing. But basically, this is what we get here. This is the velocity of the rocket relative to the frame or to the outside observer, right? So this is the velocity that we're seeing this rocket go, v, its original velocity, plus the change in velocity, equals this relative velocity. So this is the velocity of the rocket relative to the products. So if we're seeing the rocket going 10 meters per second, and then we're seeing the fuel going, say, 2 meters per second, the rocket is going to see the fuel going 8 meters per second. So this is what this relative velocity is. And then plus the velocity of the products relative to the frame, which of course is just the velocity that we as the observers observe the products going. Now what we're going to do here is we're just going to rearrange this. So we're going to subtract relative velocity from both sides. And then we're going to take this whole thing that is solved for u, so solved for the velocity of the products, and we're going to insert that into our previous equation on the last slide there. Now, once it's inserted, we're going to rearrange all that, do some algebra magic, and we get this equation, and it looks much, much nicer than it did before. So what we get right here, is negative dm times relative velocity equals big M, our original mass, times dv. Now what we can do now with this equation is we are going to divide both sides by dt, and we get this equation right here. And this is where the magic happens. Okay, so I'm going to take this equation onto the next slide right here. And so this first term that we have right here, this dm over dt, this is the rate at which the rocket loses mass, because we have a change in mass over a change in time. So we call this the mass rate of fuel consumption, and this is denoted by an R. So this R, we're just going to insert R for that negative dm over dt times relative velocity, and then also that dv over dt. That looks very, very familiar, doesn't it? If you said, yeah, that's acceleration, you are correct, right? We know change in velocity over change in time is acceleration, so we can insert acceleration here. So what we end up getting is R, our mass rate of fuel consumption, times the relative velocity is equal to big M, so our original mass times acceleration. So now this term right here, this VREL, remember, is the speed that the fuel is ejected relative to the rocket. So if the rocket is ejecting the fuel, so that's the speed the fuel is ejected. And then R is the rate at which the rocket consumes the fuel. So these two things multiplied together is actually something special as well. We call this the thrust of the rocket. So the rate at which the rocket consumes fuel times the velocity that the fuel is ejected. That's called the thrust. So what we end up getting is T thrust equals ma. Thrust is just a force. And so this is our Newton's second law equation. Force is equal to mass times acceleration. So the most important equations here are this one right here and this one right here. Okay, we're going to derive one more equation for velocity. Okay, so final velocity. So again, I'm going back to that equation 2 slides ago before before I divided both sides by dt. So that's where this equation comes from. Now we're going to rearrange this equation solving for dv. Now, the next thing we're going to do is we're going to integrate. So I'm integrating left-hand side from velocity initial to velocity final, and then integrating the right-hand side from mass initial to mass final. And then what I get here is velocity final minus velocity initial equals the relative velocity times the natural log of mass initial over mass final. So this is our other important equation in this part, or just talking about relative, systems with varying mass, is if you want to find, say, a final velocity and you have a initial mass and a final mass, or if you want to find the final mass of the rocket or something like that, and you have an initial velocity and a final velocity and a relative velocity, then you can find those things using this equation. Again, this last equation is the most important thing here. I would write that down and box it, know how to use it. We'll have a couple examples of how to use these equations that we've learned in the next couple videos.